Okay, welcome back students. We are in the third lesson of transducers engineering. As you have known, we have seen the very important characteristics and features that are necessary for the transistors engineering to start up, and till now we are not introduced to any single sensor or transducers, but we have been introduced to the what are the different types of sensors and transducers in the lesson 2. Okay, and today in the lesson 3 we are going to see again, go back to the lesson 1 continuation and see some more static characteristics and error types today. So it is transducer engineering lesson 3. So I start with what is mean by significant figures. This term is very important in any kind of engineering profession or a scientific technical area, because when you are going to represent a measurement, it's only represented in case of a number. So we need to know whether the number is significant or it's giving a meaning there. So in this case, you need to know how many digits of a number is giving a meaning, and let us see how that meaning is taken in technical terms. Now let me write the velocity of light, that is c, that is equal to 3 into 10 to the power 8. Here this 10 to the power 8 is a mere representation, and 3 is the one which gives the typical understanding for the viewer that you need a 3. Okay, so here the significant digit is only 1. Okay, this is what I trying to say. And so the significant digit here represented in 3 into 10 to the power 8 is only 1. Okay, all others are all zeros, and if you have taken out and represented is as 10 to the power 8. Okay, like that 508,444 zeros. This is another number. So how we can represent it? 508 into 10 to the power 4. So how many significant digits we have here? It's only 3. Okay. But when it comes to some things like this, 302.10, it is typically represented like this. Okay, here you cannot remove this 10. Okay, because the measurement is taken with a precision to be represented as 10. It can be also to the next measurement 11, 12, something can come out over there. Okay, so in this case you have to put the significant digits. Now we have to understand it as 5. Okay, this is another example. 302 amps. Now the significant digit is actually explicitly it is represented as 3 without any confusion. So now this is the understanding behind significant figures. The next comes static sensitivity. Now we are in the continuation mode of what are the static characteristics that we have seen in the lesson 1, and now we are going to see some more characteristics there, and we will have an understanding in it. Okay, the first one is sensitivity. Sensitivity is a relation between the output or the response of a system to the input that is given to the system. Okay, what is a system? Any system, that is, here is our sensor. Okay, here you have a system or our sensor where we are going to give an input. Okay, and you get the output or response. Okay, and here the input what we give produces the response, and the sensitivity is defined as the ratio of this response to the ratio to the input. Okay, this is sensitivity. How we can obtain this in a normal area? See here, it's something like if we are going to get some dots and then we are going to frame a line. Okay, we can create and here is our input and here is our output. How we can obtain? Very simply, if we take a slope of this thing, this line what we have, it will give us this sensitivity. So it is delta I to the delta O. So it is delta O by delta I gives the sensitivity S. This is the static sensitivity of a system. That is, gives one of the main characteristics in static characteristics. The next comes the very important characteristic of linearity. First, let me explain you what is linearity. Then we will go for saying some mathematical examples or some example based code. What is linearity in explicitly in the English vocabulary term? Something which is linear or increasing or decreasing. Okay, this is what we see in a normal. Increasing or decreasing is called as linear. Is proportionate is also another term that is given for linearity. You might have seen in your school standards or elementary secondary school education that directly proportional, inversely proportional, all these terms you might have heard and it has been told in different kinds of areas. So this proportional term directly relates to linearity. Let us take a system and we are giving in again some inputs and then we are expecting some outputs, and let me draw the system. We are giving in some, this is an input, output. For an input given, let us take the system response in this manner. Okay, so each single dot over here represent an input to the output relation. Okay, each single dot, it's a single dot. Okay, each single dot represents one reading. Okay, we are taking an input for a single, something like take, we are, this number of dots is 50 and the standard temperature, last time as I explained, standard temperature to the measured temperature, and it is the serial number, and this will go from 1 2 3 till 50, and we are taking readings from 100 degrees centigrade for a boiling point of water, and it is showing 90 and then 98. Okay, again, but it's 100 here, 100 101. Okay, here we are getting 90. So like this it goes on, and that's what we have plotted here. Okay, it's no confusion, it's simple. An input to output graph that is being plotted over here. Okay, and that gives a response in this fashion. Okay, because we can't expect a typical straight line here at the initial phase itself from our measured quantity. Here the input quantity is a standard or the independent quantity, that is from your standard temperature. This is your standard temperature or thermometer device, your laboratory thermometer, lab thermometer, and the output comes from the your measurement or your user measurement, measuring thermometer. Okay, so we are getting something like this. Is it linear? How we are going to linearize this system is what is, but it is in a increasing order. Okay, we are increasing the temperature from 100. Let us imagine we are increasing the temperature from 0 to 100. Okay, then here also there will be an increment from 0 to 100. Okay, so here it is 0, this is 100, this is 0, and it is 100, and you see there is an increment being happening from 0 to 100, but not in a typical linear fashion. Okay, its ups and downs are coming over there, but we need to convert this ups and downs into a straight line. Okay, understand, we need to convert this up and down occurring line into a straight line by using some statistical methods. You need not go in depth with the such kind of statistical methods, but there are statistical methods or regression models which convert a system into a single line, and here it is a linear system, so we call this regression model as linear regression. Okay, and if we fit a linear regression, statistical regression, this all these points will be considered and it will form a single line. Okay, now for the single line we can easily find out an equation. Yeah, true or not? For a single line, what we have made out of this points, the single line is, to simplify it and say what this regression model have done, it has contracted all the deviations and made into a some points here. That's what have happened, and it is happening using the standard deviation. Okay, and we are getting this line. Okay, this is what the method of linear regression does to these points, and finally you obtain a line, and for this line you can form the main equation, or the famous equation of the straight line, that is y is equal to mx plus c. Here your y, what is your y? Your y is your measurand or the measured temperature. Your x is the standard temperature from the thermometer, and this m is slope and c is intercept. Slope is, of course, this is your slope, delta x to the delta y, so delta y by delta x, and here you have your intercept. And you have your slope. Okay, so these are the main things that you see here. We are now able to frame an equation directly from the measured values to get the y is equal to ms plus c equation, and this equation now is a very powerful system to calibrate your sensor. Okay, now you have only from 0 to 100. Okay, but when you want some values of -10 or above 100, that is 120, you can simply substitute these values to this equation, or in between some values you are taking in the orders of 0, 10, 20, 30 degrees centigrade. Okay, but if you want 5 degrees centigrade, you can simply put inside this 5 degrees centigrade inside this equation, and you can obtain the output out of this. So this is to check the linearity and also to calibrate the system. But mainly we can see using this straight line, when what is the ideal line, what you should get, it is y is equal to x. But this is an ideal condition, you won't get this kind of a condition. Okay, instead of this you have your slope and intercept occurring over there, and the slope in this ideal condition is equal to 1 and the intercept should be equal to 0. So how much the equation is nearing to 1 or equal to 0 gives your real system. Okay, this is what I try to say, and this is linearity. So finally, to conclude, any system should be linear in nature. When you give some input, it should give an according increase or a decrease that what you have given there as the output. Okay, that is linearity of a system. Next we come the most important and very interesting static characteristic, that is the hysteresis. What is hysteresis? Think of hysteresis, everyone might have studied in your +2 and +2 grades about hysteresis, and it might have been explained in the magnetic properties of materials. And here we are going to see any system has a hysteresis behind that system. Okay, and hysteresis model is a one which gives, when you give an input to a system, okay, and when we get the output from the system, both won't be in a linear model. For that linearity only I explained it. Okay, now we will see how it behaves. We are giving in an input to the system. Let us imagine it is an ideal linear condition, it is increasing. Okay, this is what is the, we are loading the system with some input, then it's unloaded. What is this loading and unloading is, take an ammeter or a voltmeter, you are giving in current, that is loading, okay, or a voltage. Then unloading is you are slowly reducing it from the what is being given. Okay, what you expect is the same amount of reading should have been occurred from the loading and to the unloading side. Okay, but that won't occur because of the internal mechanical parts present inside the voltmeter or an ammeter. Don't take the digital meter, you take an analog meter and check it. When you give the same amount of input and take the output and then unload the output, you won't get the values. It is that kind of an effect is called as hysteresis, and you won't get the same. Actually, when you might have gotten an ideal condition, you might have received it. This is your loading, and same way it should have occurred in the unloading condition. But here it's not the case. You are giving a loading condition and then the unloading occurs in this fashion. Okay, so this is this gap, that is an error that is occurring because of hysteresis problems. Okay, now typically I told about an voltmeter or an ammeter, which is because of the internal friction. It's because of the internal friction. If you take about the outside frictional motors and all this kind of some other equipments, the hysteresis loop will look like this. You are giving in an loading, unloading, again when you load, it will look like typically in this shape. This is inputs, these are all, this x-axis is input, this is output. Okay, so this is loading, this is the unloading. Again when you load it, nothing will occur in the same fashion what it has occurred in the before condition. So this is one kind of a loop. Okay, so this is because of the outside friction that is happening. So now we are very clear about the hysteresis problems. Okay, one is because of the internal friction, then the outside friction, and also magnetic effects also produces these kind of hysteresis effects. Then we also have another types of error, that is drift. The drift condition is very simple. Let us take an input to the output. You have got some values, you linearize the value. Okay, but when you make the same measurement is made, okay, when you make the same measurement, you are not getting the points like this. The measurement is the sensor or the system is giving you a value like this. Now this is an error. Actually the ideal value should be like this, but there occurs something like this. Okay, this is called as drift. This is called as drift, and here there are two conditions involved. If you see, there is a disturbance occurring in, I can draw these lines, notice very well, see here keenly what I am drawing. This is the ideal. Okay, this can be drawn either, this is your ideal condition, but this can be drawn either like this or like this or like this. in different angles. So if there is only going to be a change in the angular conditions, then that becomes span drift. Then the other condition is something like this. The drift becomes, this is your ideal condition, but parallelly it occurs. This is called as zonal drift, and this kind of a condition where both conditions are there, okay, there is a drift in the angle and also there is a drift in the area, something like this, okay. This is your ideal condition and this is your erroneous condition, okay. This is the final condition of a multiplied problem of both span and the zonal drift occurring here. This is a drift, is one kind of a static error or characteristic because of which an error occurs, okay. Are you all very clear about the drift conditions over here? Explain a span drift, a zonal drift, and the combination of both produces a main kind of an error here. So today we have seen in this lesson a significant numbers, the sensitivity, the most important part of sensitivity, linearity, hysteresis, and then the drift conditions, okay. Now back again, we will start with again some errors. Errors are again mainly divided. Last time we saw some error conditions in mathematical terms. Now we are going to divide errors into different types and see how it looks. Errors mainly are divided into limiting errors and probable errors. Limiting errors can be defined as the ratio of error to the specified magnitude of a quantity. Okay, it is the specified magnitude of a quantity and it is represented as actual value or your value that you are measuring from your standard instruments to the measured instrument, measured value divided by the average or the nominal value into 100 when you want to represent it in percentage. Okay, these are simple definitions. Probable value is your standard deviation that is occurring because of reproducibility defects. You have to immediately imagine about the precision, because of that is the reproducibility of an instrument is only represented in precision, and this kind of a probable error occurs because of the reproducibility effects. Then comes our interesting types of error. The first one is gross error, the second one is systematic error, the third one is random error. Okay, what is gross error? The gross error is the one which is explicitly known to the user that it is occurring. Okay, that is kind of an error, that is gross error, which is explicitly known to the user. This gross errors can be mostly manually produced and it can be easily avoided by the user who is taking the reading. Okay, something like you have to take it very carefully before, if you are going to note the value of 15 by with some pronunciation mistake as 50, okay, then this can be considered as a gross error. And then also very important thing is, for every reading you have to take 3 readings and take an average, okay, so that if this, you can easily identify these kind of problems when you are going to write 15 15 50, then you will immediately you will identify there is a problem there in this 15. You can even remove this 50 and take only this 2, okay. So this is what I say. So for every reading you can go in for, this is an how to remove or an remedy for a gross error is, first thing is take it very carefully, carefulness. The second one is take average of few readings for removing the gross error. Next comes the systematic errors. These systematic errors are not produced by manual readings. It is because of produced by the instrument which is we are handling it, okay. So this can be produced very systematically and introduced inside our measurement, okay. The first thing what we are going to see is our, okay, problems in the instrument. If there is going to be a nut or a bolt loosage inside an instrument, then we can call it as a problem inside the instrument, and we have, that will create one kind of an error inside the system, okay. So this is a problem inside an instrument, and we have to recheck it, recalibrate it, all this kind of other remedies for this kind of an systematic error. The second one is measuring problems that is occurring. Overloading. There is no problem inside the instrument, but we are overloading it with, if there is only 50 bars we can measure inside an pressure transducer, and if you are going to overload with 100 bars and you are expecting something outside of the output, then that is an overloading effect. You won't get the correct results, okay. So there will be an, as we saw, there's a range and a span for an instrument, and we have to look into these kind of things, and only we have to make our measurement. So this is overloading effect, and we have our overheating, okay. We should not heat the instrument more by any kind of effects, that is the overheating effect. Then comes our most important loading effect. This you will be explicitly and also elaborately told in your linear integrated circuits in the new semesters, but here I say that any kind of electronic circuit will be put up to the loading effects by its instruments, so that in between we need some buffer circuits to avoid this kind of loading effects. That much is enough for now. For depending on the loading effects, we need buffer circuits, because you will study about this loading effects and how this can be rectified and all those things in the coming chapter, and also in your subject known as linear integrated circuits. So this is the loading effects. Then comes your most important environmental errors. You may imagine you are taking an measurement with microphone, okay. You are giving in taking a microphone, and then you are giving in some a known amount of using a tuning fork, and then you are giving in some noise to the microphone, and then you are recording the readings, and there is a building construction going on around, and it is going to give you some external noise being to the microphone. Then it will continuously, it will give you some noise inside, and it will create a problem to your measurement. So this kind of a measurement is called as a environmental error. Apart from that, imagine you are taking a temperature measurement, and there is fluctuations in your room, okay, temperature. There is fluctuations in the room temperature. Then such kind of reading also will give you very severe problems in your measurement. So only most of the laboratories should be maintained in air conditioned rooms, so that you get a constant temperature inside the room, so the room temperature don't affect your precise measurements. So these are environmental errors. The fifth one is, everyone might have seen, observational error. When you take a reading, okay, this observational errors can occur. Constantly taking readings, it is, don't compare this observational error with the gross error, okay. You are constantly taking a reading, a wrong reading, which is going to give you an erroneous result continuously, okay. From starting number 1 to 50, if you are going to take, then that's an observational error. The most interesting error for this is parallax error. The parallax error, very well you might have studied in your 12th standard. Again, when you have your ammeter or a voltmeter system with an analog pointer, okay, when you are going to have your eye at any angle, we are going to read your using your eye at any angle, you will get a wrong reading. You have to keep your eye exactly at the center and you have to read the pointer, okay. Even to the left, you will get a right error. When you keep it to the left, you will get a left point parallax error. You have to keep it to the straight upside region and you have to take the pointer value, okay. So this is an observational error which will be repeated in your measurements and it will create a final problem of erroneous result. So now we have seen the systematic error as a different 5 types. Here we have seen the gross error, 2 types, and five types of systematic error, and finally we comes to the random error. Random errors are generated by not by any kind of this gross or a systematic error. Simply random errors are generated by means of any other kind of sources. Any other kind of source error is a random error. In between, suddenly we don't know how it can be rectified. Such kind of errors can creep inside. That's are called as random errors. Now, finally we come to the mathematical part, how we are going to estimate these errors by few parameters. You might have known all these are very simple things. Mathematical estimation using few parameters. The main parameter is mean. Let us take you have x1, x2, x3 are your values till xn, okay. First is mean. Take the mean of 10 values are there, means x1 to x10 divided by 10 is your mean. Then average deviation. Average deviation is what is the deviation of each value. This is your mean value and you have all your values here, and what is the average deviation from the mean value? How are you calculating it? x1 is your value minus x bar, that is your mean value, will give the average deviation d1. Like this you have to calculate it till d10, okay. This is your average deviation. Then you have the most important standard deviation. Standard deviation at there is the next important concept, SD. You might have studied all these things in your schools, I hope. This the epsilon of d square divided by n minus 1 is your standard deviation. You have to find it out. You have your average deviation, you have to accumulate it over here and divided by n minus 1 to the root. This gives you the standard deviation. Finally you have your variance, which is the variance, standard deviation square, that gives the variance, okay. All other systems are probable. The error calculations that we have seen last time, okay, the cumulative error, the limiting error, all these things also can be calculated. Then how much frequently a single reading occurs. If you have 50 readings, how much frequently that's occurring, that also you can take. Frequency of a reading, that's also can be taken. So these are some mathematical terms that can be taken for the expressions. So today we have seen different kinds of errors, all this limiting error, probable error, gross error, systematic error, random error, okay. And most importantly, we have seen some many different static characteristics that completes all different kinds of static characteristics, like linearity, hysteresis, drift, okay. Then the significant digits we have seen, okay. So all these things are very important before we enter our sensor session in the static side, okay. So next class we will continue with our dynamic characteristics, and that will complete our unit number 1. Then we will can enjoy our journey of sensors engineering from the second chapter. Thank you.